Welcome to the 7th session of this integration series. In this session, integrals with the following integrand will be dealt with: logarithmic functions, inverse trigonometric functions, sine, cosine, and tangent functions, miscellaneous elementary functions. We will present 6 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the 7th session of this integration series. There are 2 antiderivatives to determine in example 1. As for the first one, since the differentiation of Ln of 1 plus x all over the result of 1 minus x can be done by using chain rule and quotient rule, it equals 1 minus x all over the sum of 1 plus x multiplies 1 minus x plus 1 plus x all over 1 minus x all in parentheses squared, which can be simplified to 2 over the result of 1 minus x squared. Hence, d ln of 1 plus x all over the result of 1 minus x all in parentheses equals 2 over the result of 1 minus x squared dx. So, the entire derivative equals 1 over 2 times the integral of ln of 1 plus x all over the result of 1 minus x d ln of 1 plus x all over the result of 1 minus x all in parentheses, which equals 1 over 4 times the square of ln of 1 plus x all over the result of 1 minus x all in parentheses plus c. Here we continue to work on the second antiderivative of example 1. Here we apply the chain rule along with the quotient rule of differentiation. So the differentiation of arctangent 1 plus x all over 1 minus x all in parentheses equals the reciprocal of 1 plus the square of 1 plus x all over 1 minus x all in parentheses multiplies the differentiation of 1 plus x all over 1 minus x all in parentheses. After being simplified, it equals 1 over the sum of 1 plus x squared. Hence, d arctangent 1 plus x all over 1 minus x all in parentheses can be written to 1 over the sum of 1 plus x squared dx. Hence, the antiderivative can be written to the integral of arctangent 1 plus x all over 1 minus x all in parentheses d arctangent 1 plus x all over 1 minus x all in parentheses, which equals 1 over 2 times arctangent 1 plus x all over 1 minus x all in parentheses squared plus c. Example 2 is to find general solutions of 2 antiderivatives. As for the first antiderivative, since the integrand can be written to the square of sine x over 2 plus 2 sine x over 2 cos x over 2 plus the square of cos x over 2 all over the sum of 1 plus 2 sine x over 2 cos x over 2 plus 2 times the square of cos x over 2 minus 1, which is simplified to sine x over 2 plus cos x over 2 all in parentheses squared over the product of 2 cos x over 2 and the sum of sine x over 2 plus cos x over 2. Hence, the antiderivative can be written to 1 over 2 times the integral of sine x over 2 plus cos x over 2 all over cos x over 2 dx, which equals the integral of tan x over 2 dx over 2 plus 1 over 2 times the integral of dx, which equals negative ln of the modulus of cos x over 2 plus x over 2 plus c. Here we continue to work on the second antiderivative of example 2. We first let tangent theta equals x plus 1, which gives the x equals 1 over the square of cos theta d theta. Hence, the antiderivative is written to the integral of the reciprocal of the product of x plus 1 all in parentheses squared and the square root of the sum of x plus 1 all in parentheses squared and 1 with respect to x plus 1, which can be written to the reciprocal of the product of tan squared of theta, sec theta, cos squared of theta, d theta, which equals the integral of cos theta over the square of sine theta, d theta, which equals negative 1 over sine theta plus c. Since tangent theta equals x plus 1, 1 over cos squared of theta equals x plus 1 all in parentheses squared plus 1, which gives sine theta equals the square root of 1 minus 1 over the sum of x plus 1 all in parentheses squared and 1, which equals x plus 1 all over the square root of x squared plus 2x plus 2. After being substituted back to the variable x, the antiderivative equals negative 1 over sine theta plus c, which can be expressed to negative square root of x squared plus 2x plus 2 over the sum of x plus 1 plus c, which is the general solution of this anti-differentiation. Example 3 is to find an indefinite integral of x squared over the square root of a squared minus x squared dx. We start to let x equals a sine t, which gives t equals arcsine of x over a and dx equals a cos t dt. Hence, the antiderivative is written to the integral of the square of a sine t over the square root of a squared minus the square of a sine t multiplies a cos t dt, which equals a squared times the integral of sine squared of t dt, which equals 1 over 2 times a squared t minus 1 over 4 times a squared sine 2t plus c. Since sine 2t can be written to 2 sine t cos t, which equals 2x over a multiplies cos arcsine of x over a, which can be further simplified to 2x times the square root of a squared minus x squared over a squared. Hence, the antiderivative can be written to 1 over 2 times a squared arcsine of x over a minus 1 over 4 times a squared 2x square root of a squared minus x squared over a squared plus c, which equals 1 over 2 times a squared arcsine of x over a minus 1 over 2 times x square root of a squared minus x squared plus c. Example 4 is to find a general solution of the integral of the square root of 1 minus x squared all in parentheses cubed dx. We start to let x equals sine theta, which gives theta equals arcsine of x and dx equals cos theta d theta. Hence, the antiderivative is written to the integral of the square root of 1 minus sine squared of theta all in parentheses cubed times cos theta d theta, which is simplified to the integral of cos to the fourth theta d theta. Then we may repeatedly apply the double angle formula to bring down the power of the cos to the fourth of theta. So the cos to the fourth of theta is finally simplified to 1 over 4 times cos 4 theta plus 1 all over 2 plus 2 cos 2 theta plus 1 all in parentheses. Hence, a general solution of the antiderivative equals 1 over 4 times sine 4 theta over 8 plus sine 2 theta plus 3 theta over 8 plus c, which can be further simplified by applying the double angle formula to sine 2 theta cos 2 theta over 16 plus sine 2 theta over 4 plus 3 theta over 8 plus c. Here we continue to work on example 4. Since the antiderivative can be written to sine 2 theta over 16 times cos 2 theta plus 4, or in parentheses plus 3 theta over 8 plus c, and sine 2 theta can be written to 2 sine theta cos theta, which equals 2x times square root of 1 minus x squared, and accordingly cos 2 theta can be written to 1 minus 2 sine squared of theta, which equals 1 minus 2x squared. Hence, the general solution of the antiderivative equals 1 over 16 times 2x square root of 1 minus x squared times 1 minus 2x squared plus 4, or in parentheses plus 3 arcsine of x over 8 plus c, which is finally simplified to 1 over 6 times x square root of 1 minus x squared times 5 minus 2x squared, or in parentheses plus 3 arcsine of x over 8 plus c. Example 5 is to determine a general solution of the integral of square root of x squared minus 1 over x to the 4th dx. We start to let u equals 1 over x, which gives du equals negative 1 over x squared dx, and dx equals negative 1 over u squared du. Hence, the antiderivative can be written to the integral of square root of 1 over u squared minus 1 over 1 over u to the 4th times negative 1 over u squared du, which equals negative integral of u times square root of 1 minus u squared du. Now, we do the substitution again and let u equals sine theta, which gives du equals cos theta d theta. Hence, negative integral of u times square root of 1 minus u squared du is written to negative integral sine theta square root of 1 minus sine square of theta times cos theta d theta, which can be simplified to the integral of cos square of theta d cos theta, which equals cos cubed of theta over 3 plus c, which is 1 over 3 times square root of 1 minus sine squared of theta, or in parentheses cubed plus c. After being substituted back to the variable u, it equals 1 over 3 times 1 minus u squared, or in parentheses to the power of 3 over 2 plus c. After being substituted back to the variable x, we have the simplified general solution of the antiderivative, which is x squared minus 1, or in parentheses to the power of 3 over 2 over 3 x cubed plus c. Example 6 is to find an antiderivative of the integral of x plus 1 all over the product of x squared and square root of x squared minus 1 dx. We start to let u equals 1 over x, which gives du equals negative 1 over x squared dx. Hence, the antiderivative can be written to the integral of 1 over u plus 1 all over the product of 1 over u and square root of 1 over u squared minus 1 multiplies negative 1 over u, or in parentheses squared du, which is simplified to negative integral of 1 plus u, or over square root of 1 minus u squared du. Again, here we let u equals sine theta, which gives du equals cos theta d theta. Hence, negative integral of 1 plus u all over the square root of 1 minus u squared du is now written to negative integral of 1 plus sine theta all over cos theta times cos theta d theta, which is simplified to negative integral of 1 plus sine theta or in parentheses d theta, which equals negative theta plus cos theta plus c. After being substituted back to variable u, the entire derivative becomes negative arcsine of u plus square root of 1 minus u squared plus c. Then, after being substituted back to the variable x, the entire derivative equals the square root of 1 minus 1 over x squared minus arcsine of 1 over x plus c, which is finally simplified to square root of x squared minus 1 all over x minus arcsine of 1 over x plus c. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.